October 21st, 2025. A solar storm explodes on the far side of the Sun, its shockwave traveling at nearly 2,500 kilometers per second. At the same moment, interstellar object 3I/Atlas is hidden in direct alignment behind our Sun, caught between Earth and a cosmic blast no telescope can yet see. The official forecast warns of radiation storms and rising geomagnetic danger, but as 3I/Atlas races toward its closest approach, no one can yet explain what happens when an alien visitor is supercharged by our star. Today, we break down the evidence and reveal why this event could reshape how we understand interstellar objects forever. At 2000 hours UTC on October 21st, the ACE spacecraft at L1 began transmitting data that caught the attention of every space weather desk on the planet. Electron flux levels, usually steady, surged by more than a factor of 10 in less than 2 hours. The charts didn't just rise, they spiked, climbing from background values to readings consistent with a strong solar energetic particle event. This wasn't a slow build, it was a wall of high-energy electrons arriving ahead of the expected proton storm, a sequence well known to forecasters as the classic signature of a major solar eruption in progress. The timing was unmistakable. The electron surge began just as the far side CME's shock front was modeled to cross the interplanetary magnetic field lines that connect the Sun to Earth's orbital neighborhood. Radiation storm criteria were met almost instantly. By 2200 hours UTC, the NOAA Space Weather Prediction Center had issued a solar radiation storm watch, warning of S1 to S3 conditions, meaning mild to strong radiation levels, enough to trigger alerts for satellite operators and polar aviation routes. For reference, S1 can disrupt minor satellite functions and prompt extra monitoring, while S3 brings elevated risk for single-event upsets, surface charging, and radio blackouts at high latitudes. The differential timing of electrons and protons is more than a curiosity. Electrons, being lighter, travel faster along the Sun's magnetic field lines, arriving hours before the heavier protons. This early electron spike acts as a harbinger, signaling that the main event, the proton-rich solar storm, will soon follow. Spacecraft teams scrambled to review protocols, and commercial satellite operators braced for possible anomalies. At the same time, ground-based cosmic ray detectors prepared for what could be a classic Forbush decrease, as the incoming shock swept away galactic background particles. The scale of the hazard was immediate and global. Electron flux up by over an order of magnitude, proton levels rising, and the world's attention locked on the Sun-Earth line. The question on every expert's mind: what unleashed this energetic barrage, and could it be traced to the violent eruption now racing toward Venus and the hidden interstellar visitor beyond? On October 20th, 2025, the solar system's geometry delivered a rare blind spot. While the world watched radiation levels spike, 3IAtlas slipped directly behind the Sun from Earth's perspective. This is the moment of superior conjunction, a configuration where the Sun stands between Earth and a distant object, blocking all direct observation. At the same time, the Moon reached its new phase, lining up almost perfectly with the Sun and Earth. The result? A straight invisible line stretching from our planet, through the Moon, to the Sun, and out to 3I/Atlas, now hidden on the far side. This kind of cosmic alignment isn't just a curiosity for orbital diagrams. With both the new Moon and 3I/Atlas in conjunction, the usual tools, ground-based telescopes, even most space observatories, lose their line of sight. No visible light, no infrared, not even radar can cut through the glare and plasma of the solar disk. For a brief window, the interstellar visitor becomes a ghost, unreachable by direct observation, its fate tied to whatever solar activity is unleashed on that side of the Sun. The timing is more than coincidence. As the CME erupts from the far side, its trajectory points almost directly at the unseen 3I/Atlas. The comet's path, nearly aligned with the ecliptic, brings it into the crosshairs of the solar storm, just as it's most exposed and least observable. For planetary scientists and heliophysicists, this is a collision course hidden in plain sight, one that can only be reconstructed through indirect evidence, modeling, and the delayed arrival of energetic particles. On the ground, astronomers mark the date: October 21st, new moon, superior conjunction. They know that in the darkness behind the sun, an interstellar object is about to be struck by the full force of a solar eruption, and the only clues will arrive in the data, hours or days later, filtered through the sun's relentless glare. On the night of July 1st, 2025, a faint moving point of light triggered an alert in the Atlas survey's automated pipeline at the Cerro Pachon Observatory in Chile. The system flagged its trajectory as unusual, but it was a junior team member, an amateur astronomer volunteering on the project, who noticed the numbers didn't fit any known comet or asteroid. The object's path was steep, cutting back against the flow of the planets, and the orbital calculations refused to close. Within hours, the team submitted their finding to the Minor Planet Center, and within days, observatories worldwide were racing to confirm what the data suggested. This was no ordinary visitor. The designation followed quickly: 3I/Atlas, the third confirmed interstellar object to cross the solar system, after Oumuamua and Borisov. Its orbit was hyperbolic, meaning it wasn't bound to the sun and would never return. The numbers were striking: a tilt of 175 degrees, skimming the plane of the planets but moving in the opposite direction, and an inclination just 5 degrees off the ecliptic. Early projections showed it would pass near Mars in October, then swing closest to the Sun at 1.36 astronomical units on October 29th, moving at nearly 68 kilometers per second. There was no threat to Earth. Its closest approach would be 1.8 astronomical units, a comfortable gap. But its interstellar origin made it a rare prize. For the Atlas discoverer, the weeks that followed were a blur of interviews, late-night data sessions, and a sudden leap from anonymous survey work to the center of a global scientific event. 3IAtlas is now enduring a transformation that only a handful of objects in the solar system ever experience. As it races inward, its exposure to sunlight has increased by more than 7 million times since it was drifting in interstellar darkness. The numbers are stark. What began as a trickle of energy, less than a millionth of a watt per square meter, has become a flood, with the comet now absorbing around 735 watts per square meter as it closes in on perihelion. This leap in irradiance isn't just a statistic. It's a physical shock to the nucleus, driving rapid changes in temperature, chemistry, and surface structure. Observatories tracking 3IAtlas before it slipped behind the sun recorded a dramatic rise in outgassing. By mid-September, hydrogen cyanide production had tripled, reaching about 4.5 times 10 to the 25th molecules per second. The coma swelled and the dust tail grew more pronounced, hinting at volatile ices boiling off as the comet's crust fractured and vented. Such activity is typical for comets approaching the Sun, but 3IAtlas is not a typical comet. Its interstellar origin means it carries exotic ices and a chemical fingerprint unlike anything orbiting our star. The timing could not be more precarious. With the CME's shock front barreling toward its position, 3IAtlas is about to be tested by an environment that pushes even native solar system comets to their limits. The stakes are real. A sudden jolt of energetic particles and magnetic turbulence could trigger unpredictable outbursts or even structural changes. While Earth remains safely distant, no closer than 1.8 astronomical units in December, the interstellar visitor now stands exposed, its fate tied to the Sun's volatile mood. Sunspot regions 4245 and 4246, both unusually active, dominated the solar disk in the days leading up to October 21st. Their magnetic fields churned with complex, interlaced loops, prime territory for the kind of instability that precedes a major eruption. As these regions rotated over the Sun's eastern limb, observers noted a steady climb in X-ray flux. By October 20th, the most volatile group had just slipped out of direct view from Earth, but its influence lingered. At 2024 Coordinated Universal Time on October 21st, the Solar and Heliospheric Observatory's LASCO C2 coronagraph captured the first signs of upheaval. A bright, asymmetric halo began to bloom, spreading rapidly across the instrument's field. Unlike the classic uniform ring of a symmetric coronal mass ejection, this event pushed outward in a lopsided arc. The bulk of the material surged off the far eastern limb, a clear indicator that the eruption was both powerful and directed away from Earth. Stereo A, stationed well off the Sun-Earth line, offered a crucial side-on perspective. Its HI and QR images tracked the coronal mass ejection's expansion, revealing a dense front moving at over 2,400 kilometers per second. The blast's origin traced back to the coordinates of old active region 4246, now hidden on the far side. NASA and ESA space weather analysts, reviewing the data in real time, confirmed the eruption's trajectory, not toward Earth, but squarely in the direction of Venus, and by extension, the path of 3IAtlas. The evidence was unambiguous. C2 and C3 coronagraphs displayed the full scope of the blast, while Stereo A's vantage confirmed both the speed and angle. Analysts mapped the propagation cone, overlaying it on ephemeris plots. The alignment was striking. The coronal mass ejection's shock front, modeled with high confidence, would intersect the orbits of Venus and the interstellar comet within days. For the first time, the threat could be traced, step by step, from the tangled magnetic fields of a sunspot through the expanding corona to a precise sector of the inner solar system. This is the foundation for every forecast and every alert issued in the hours that followed. Forecasting the path of a solar eruption across the solar system is a test of both physics and timing. As soon as the far-side coronal mass ejection left the Sun on October 21st, propagation models like Enlil were tasked with predicting the shock's course and impact windows. Analysts input the CME's measured speed, nearly 2,500 kilometers per second, and launch coordinates from Stereo A and SOHO, then ran scenario after scenario to map its trajectory. The results converged on a clear outcome. Venus and 3IAtlas stood directly in the line of fire. Model outputs showed the shock front would reach Venus between 0600 and 1600 Coordinated Universal Time on October 23rd, with the comet's position just hours behind. Estimated arrival between 0800 and 1800 Coordinated Universal Time the same day. The sheath of compressed plasma and tangled magnetic field would follow, overtaking the comet within the next 6 to 12 hours. The core of the CME, likely carrying a strong southward magnetic field, trailed close behind. Each phase, shock, sheath, core, brings its own hazards. Sudden increases in particle flux, swings in magnetic orientation, and the potential for intense, localized turbulence. For 3IAtlas, the encounter would be nearly head-on, with the shock normal aligned closely to the Sun-comet line. The uncertainty in these predictions, about 8 to 12 hours, comes from the subtle drag of the solar wind and the expansion angle of the CME itself. Yet confidence was high. The propagation vector, tracked through coronagraph and heliospheric imager data, left little doubt about the alignment. Earth, by contrast, would be spared a direct hit, experiencing only a glancing blow of energetic particles and a classic Forbush decrease as the shock swept past. As the countdown to impact narrowed, the focus locked onto a tight window. October 23rd, with the fate of Venusian spacecraft and the interstellar comet hanging on the model's margins. For scientists, it was a rare chance to watch a cosmic chain reaction unfold, timed to the hour, mapped across millions of kilometers, and set to deliver its verdict in data yet to arrive. Satellite operators across the globe spent the hours after the coronal mass ejection alert in a state of heightened vigilance. As the first electron spikes registered at monitoring stations, commercial networks initiated precautionary protocols. A senior instrument scientist at a major European geosynchronous satellite consortium recalls the moment. "We didn't see a trigger for automatic safe mode, but the charging rates on the outer panels shot up by nearly 40% over baseline. Our team watched the telemetry like hawks." In low Earth orbit, a weather satellite reported brief but measurable surface charging, enough to warrant a temporary science data hold. No major outages occurred, but the risk was real. High-frequency radio operators, especially those supporting transpolar flights, logged several minutes of degraded signal quality. One northbound flight over the Arctic reported a short-lived high-frequency blackout traced by aviation meteorologists to the ongoing solar energetic particle event. Meanwhile, out at Venus's orbit, the Parker Solar Probe and Bepi-Colombo relayed bursts of particle data back to Earth. Both spacecraft registered transient spikes in proton and heavy ion counts as the modeled coronal mass ejection front swept past. The Parker team's lead instrument scientist noted a sharp, hour-long jump in local radiation, aligning almost exactly with the predicted shock arrival time. Bepi-Colombo's magnetometer recorded a sudden magnetic field swing, followed by a pulse of plasma wave activity. These signatures confirmed the models. The coronal mass ejection's shock and sheath had indeed crossed hardware, not just theory. For ground teams, the data provided rare, tangible proof that the forecasts were not just academic, they were being played out in real time, with spacecraft and aviation systems on the front lines. Just after midday on October 21st, two magnitude 4.5 earthquakes struck near Katowice, Poland, 8 minutes apart. That evening, a 3.9 tremor shook Scotland's northwest coast. No injuries, no damage, just a flurry of online theories. The timing, so close to the CME's eruption and the passage of 3IAtlas, fueled speculation. Could a solar outburst trigger quakes on Earth? Social media posts multiplied, echoing a question that's lingered for decades. Seismologists responded quickly. The USGS and British Geological Survey pointed to tectonic stress, not solar storms, as the cause. They referenced decades of seismic records, showing that while Poland's twin quakes were unusual in timing, they fit established regional patterns. Academic reviews, peer-reviewed, and open access have consistently found no mechanism linking coronal mass ejections or solar energetic particles to earthquakes of this scale. The data, they said, simply doesn't support the theory. Still, the idea persists. A few researchers continue to search for subtle links, suggesting rare electromagnetic effects might nudge faults already near failure. Most scientists remain skeptical, attributing any overlap to coincidence and the sheer frequency of both solar storms and earthquakes. The 2017 M8.2 Mexico quake, which followed Oumuamua's perihelion, is often cited by enthusiasts, but mainstream geophysics sees only chance. A similar divide shapes the debate over 3IAtlas. Some propose the CME might supercharge the comet, causing outbursts or chemical changes. Veteran comet scientists urge caution, noting the vast difference in scale and the lack of direct evidence. For now, the comet's fate remains hidden behind the Sun. The arguments are unresolved, the data incomplete. The next observations may clarify or deepen the mystery. At 2024 Coordinated Universal Time on October 21, 2025, a far-side solar coronal mass ejection erupted with a shock speed near 2,474 kilometers per second, confirmed by C2 and C3 coronagraph imagery and stereo A observations. This event coincided with the superior conjunction of 3I/Atlas, placing the interstellar object directly behind the Sun from Earth's view and exposing it to an estimated solar irradiance surge from below 10 to the -7th to about 735 watts per square meter. NASA's Enlil models project the CME shock to cross 3I/Atlas's trajectory within 2 days, but the specific effects on its chemistry or structure remain unobserved. While satellite and probe data confirm a spike in high-energy particles, and seismic events in Poland and Scotland were catalogued during this interval, no direct causal link to solar activity has been established. The closest approach of 3IAtlas to Earth is scheduled for December 19, 2025, with both bodies moving in broadly the same direction. As new data arrives, the scientific community continues to watch for measurable changes, but many questions about how interstellar objects respond to extreme solar events remain unanswered.